Okay. People are reading. But the first thing I want to show you is waves. Okay? It's very important to study waves. So now we're all going to make sounds. Woo! Ah! Yeah, woo! Ah, then we can, we can get really, so we can clap. Yeah? Yeah, okay, good. All right. We stomp. We'll mess up all the data downstairs. Okay, we can go twice. 1, 2. Yeah. Okay. There's a way to get people's and students' interest, and that's to do silly things. So you ready to go? Physics is a joy, make a big noise, playing in the class, gonna be a success someday. We got chalk on our face, there's no disgrace, slamming that science all over the place, singing. Yeah, one more. All right, so that loosens everybody up a little bit. We don't want uptightness. Okay, so what you see is we have sound is made of waves, okay? Woo, you know, and then, that's a very important thing because not only is sound made of waves, but light is made of waves. So since we have people here that teach all levels of class, I'm going to even go to the crazier parts of a show. I need a volunteer. Okay, come on. If you guys were in like 3rd grade, everybody going, me, me, me. Where's the child in you? Somebody volunteer? Ah, talk. All right. And your name is? Yuan. Thank you, Yuan. Okay, Yuan, you got your name correctly. Very good. Back up, be careful. Get close to Anna there, and we'll try to make this as good as we can. Okay, so what I'm going to do is I'm going to send information to you and energy to you because what waves do is transmits energy from one place to another. So I can make Yuan's hand move without going over there to shake it. Just go like this. See? His hand moves because I put energy in, and that energy gets transferred by the wave pulse. Okay? There. Okay? And now it's interesting because the wave goes and comes back, and it reflects. Okay? And if I figure out the time it takes for that wave to go back and forth, like 1, 2, 3, 4, 5, and if I move this at that same rate, 1, 2, 3, 4, 5, I get a special wave. I get the standing wave. I'm now resonating with the time it takes the wave to move back and forth up this spring. I'm giving it energy at that same thing. We call that resonance, huh? And that's a standing wave, yeah? And that's the first harmonic in sound, yes? And then if I just would now double that rate, no, you hold still, Yuan. There we go. We double the rate, and I get the next harmonic, yes, okay? And then if I triple it, I get the third. And what we start seeing is this is a higher frequency. So if I, first I can measure the wavelength, which would be the distance between like those 2 points that aren't, actually it's the distance between a peak and a peak. So we have 1.5 wavelengths right now, okay? You can picture 1.5 sine waves, yes? And you might notice that I'm getting a little tired because the higher the frequency, the more energy I have to put into it. So the energy is related to the frequency, and the frequency is how many times per second something oscillates. So if I would can you come over here, right there? And I want you to sort of stand in the center here, just sort of squat down in the center. Just you can kneel down. No, I want your head. Yeah, that's fine. No, that's fine. Okay. We see it's hitting our hand. Now just let it stand still. And the frequency is how many times per second does it hit her hand? Okay? And the unit is the hertz because it hurts when it hits her hand. What's life without humor? But okay, so that's the hertz. So if I double the frequency, then it's twice as many per second, and that's the hertz, and that's the frequency. And if I start getting the energy going now, and I get 3, ow, 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 ow. And if I get 4, can I get 4? Oh, wait, and we can see it's taking more energy to do that, and it hurts more. Okay, all right, okay, thank you, Yuan, and Caroline, okay, talk. Okay, so now we see that we have frequency, we have wavelength, energy is related to the frequency, and we're going to move from there. So in musical instruments, that oscillation, those resonances, play notes on a, okay? And if I would shorten the string, then it's going to oscillate faster because the time it takes to travel back and forth is less. So it. Okay, anyway, I can actually, anyway, that's all right. I won't play. But the string instrument all works on these standing waves, and we can change frequencies. And we get a particular note when something oscillates at a very particular frequency, okay? And this is how we do sound and music, okay? And with that, we can try to play music and musical instruments, wind instruments. And lately, this what's happening nowadays is we get an interesting type of music, which my son has just been turning me on to. And I just have to find my proper, this is what I forgot to do. See, this is going to happen every once in a while when I can't, when I'm panicked. I'm looking for a particular piece of software that should be down here. There it is, okay? And then I can quit this one. I can leave it. I'm going to open this up. This is a piece of software that runs on a Macintosh, and it's called the Signal Suite. And it basically is a signal generator software. And I have to plug this in here now and make sure that this is turned on. Okay, we got that. And let's see if I'm working. Okay, yep, okay, we got it. All right. So there are frequencies that you have with a wave, like hopefully this won't be too loud. If it is, watch your ears. Okay, all right. So, okay, and if you just change the frequency, you change the pitch, yes? Okay, all right, so we got all that. So you all know that. But if we also do, lately, how many people are familiar with what's listening to music these days called dubstep? Any dubsteppers out there? Anybody know these things about DJs doing mixing and stuff? Okay, if you're teaching high school and middle school, you better go out and listen to a little dubstep, speak the language of your students, okay, because this is happening now. My son, 15 years old, is doing all this stuff. And I was observing him. Has anybody seen videotapes of dubsteps? Where they have a guy with a Macintosh computer doing this, and everybody's doing this with their hands, and everybody's doing this, and everybody's, you know, and this guy is standing there, and he's just turning knobs, and he's doing stuff. Well, I was trying to figure out what is he doing, and I watched my son, and here's what he's doing. And I'm going to use a noise signal here. Okay? And that's the noise signal, and here is the frequencies of everything you're hearing, okay? So what you can do is change the sound. There, all the low end is gone. It's just the high end, okay? And you can get the low end back. You can take the high end out, all right? Just have the low end, okay? You can actually do notch filters. Okay, so all these modern day music is just taking these frequencies and these pitches and changing it. Why am I telling you this? Because it's something new, it's something interesting, but there's physics behind it. And you try to tell your students about, oh, you got to learn the physics, and they get bored and they don't know what you're doing. Hey, dubstep. Did you know dubstep is just a matter of a bunch of notch filters and taking out the harmonics and the frequencies and changing it, and what you're doing with timing and stuff? It's all physics. It's all right there. So, and if you watch the DJ, they always have some music that builds up to some big climax. And it hits that climax, and then it gets very exciting. And the music sounds like, now here's what I want you to remember. But let me go back to Signal Suite just for a second. Where did it go? Come back wherever you are. Okay, it's hiding in the back there. Okay, so if I do that, so you have a DJ, and they get up and they get really excited, and there's a thing called the drop. And it goes, boom, and the DJ kind of goes like this, and then right when that drop happens, they do something down here, and they go crazy, and everybody goes, wow, and it's just all very exciting. Here's what the DJ does. Are you ready? That's exactly what they're doing. That's exactly what they're doing, but they're doing it in a little more of an exciting way. Are you ready? Here we go. And my son mixed this for me. And then they can go around with this frequency, and then they'll take out the high end right here. Same thing. And then they mellow out and they chill for a while. For the excitement of music and rock and roll, you have this types of, come on. There, you have the lights flashing, and with this, with this, no lights flashing. Okay. So the biggest, the one part of the music, and then the other part is the lights and the colors of the lights. And you guys were playing with this before. This is a what's now called an LED floodlight. You can actually, they're using these in landscaping and lighting up buildings, and you can change the colors. But it's 3 LEDs, red, green, and blue LEDs. And if you just put a slit here, you can actually see the 3 LEDs that are lighting up to make all those different colors. And from looking over here, you can have these different combinations of colors that are happening is just a mixture of red, green, blue, because that's what our eyes see. Yes? Okay? So, and this is what's making all these different colors. But light is a very interesting, strange phenomena, and it's really kind of weird. If I can just turn this off. Okay. So I'm going to bring out a laser here now, and I'm going to have this green laser. And what I want to do is I'm going to point this green laser at the board up there. So let's go ahead and do that. Ready? Here we go. Let's try to get that green laser on there. Okay, there. Now you see that green laser dot, yes? And you can see the green laser dot is happening because of the light coming from my hand to the wall, okay? But there's a very strange thing about the light coming from my hand to the wall is you cannot see the light as it travels from my hand to the wall. All right? And this is like the sun. The sun is shining out there. It's very bright, but space is dark. It lights up the earth, but space is dark. So space looks dark except for the sun lights up the earth. So you can see the light where it interacts with something, but you can't see it when it's traveling from one thing to another. Why can't we see that electromagnetic wave? That seems kind of odd. Unless some particle gets in the way, like the moon. Then we see the light again, because the light hits the moon, and then we see the moon lit up, but we don't see the light traveling from the moon to the earth unless it interacts with something on the earth, like the atmosphere or something. And that is one of the strangest things about light itself. Why does that... Wait a second. Where's that light coming from? Well, to find out where the light's coming from, I better interject some particles in the air. So let's see if we can go up here and interact some... we're zeroing in on the light here. Anna's got the light. Okay, all right. So that's the other part of the rock and roll concert, right? They fill the stage with all the smoke and the haze and theater haze, so you can see the lights and makes it a much more exciting environment. But isn't that strange thing about light that you can't see it where it travels unless there's some particles or something for it to interact in the air? So that's another fun thing about light. Yes. What else should I do today? Oh, let's play with this one, shall we? We can turn the lights back on for a little bit. There's another phenomena of light, and that is, you can see stuff, okay? Anytime you see something like this glass, what's happening, you might think, well, yes, I see the glass because light's reflecting off of you might think of it as a light ray bouncing off. But that's not what happens at all, right? The light ray comes into the glass vibrates and shoots the light ray back out, because light is always vibrating electrons. And what's happening here is the speed of light is changing, and so it's bending, and so that's why you can actually see the glass, because the speed of light is actually speeding up and slowing down as it goes through the glass. But glass also has an interesting, you learned about crystallography today, and glass is basically a crystal of molecules all put together, and they have this sort of very structure that's made this glass test tube, okay? And at the university, students go through chemistry, they break a lot of these things, and it gets very expensive, so we try to find a very cheap way of trying to replace these. And so we came up with a fluid here that can actually help mend glass. So if I just break this glass, okay, there I broke the glass. Oh, poor me, I broke the glass. And now I'm going to put this glass in this fluid here, okay? And one piece of glass on the floor. Everybody be careful. No bare feet, please. Okay? And then I have to find something to be able to pull the glass out with, and I had a pair of tongs. Here they are. Okay? And now I mix I wait just a little bit. Now remember that glass had that crystalline structure, right? So it's like springs, right? It should just all come right back together if we can just find the right fluid for it to mix with. And so we go in there and we go and, yes, it came back together just fine. So we just actually manufactured a new piece of test tube. Yeah? Yeah? Very clever, huh? Okay. But the biologists are very clever, actually. If you just put one piece of glass in, a biological fluid will actually make clones. So we can just actually make all kinds of test tubes of different shapes and sizes. And it's actually kind of fun here. And we got another one down here. Okay. All right. Anyway. Of course, that's a trick. So what's the trick? Well, the trick is that, remember I told you that the speed of light changes and it makes the glass appear to you. But if you put it into a fluid that the speed of light does not change, the light cannot bend and you will not see it. So this is the beauty of this. And we'll try and do this. I'll even get some oil on my fingers and I'll hate myself the rest of the show, but I'll try to do this as best I can. Okay, everybody can see the test tube? Because there's air inside it, yes? So you have the light going from the glass through this oil, through the oil to the glass and into air. But if I replace that slowly but surely with the oil, okay, the test tube basically essentially disappears. This is vegetable oil, just olive oil or safflower oil, vegetable oil, and Pyrex. So you too can do this with your students. Just go to the store, vegetable oil, but you got to make sure you have Pyrex test tubes. And then another trick, if you don't want the Pyrex word to show up in the oil, scratch off all the paint that says Pyrex on it, and those scratches will fill up with the oil, and you still won't see it when it's submerged, even the scratches. So, okay, so that's a matching index of refraction, basically, demonstration. So, did you catch it on the camera okay? Yes, the disappearing test tube? All right. Okay. So that's always a nice thing to talk about students and talk a little bit about either show them and ask them, why is this happening? And hopefully you've explained index of refraction a little bit or bending of light, and all of a sudden the light's not bending. All right. Okay, now what else do I have here to do today? What time is it? Okay. Did a little bit of the color mixing. Oh, yes, what makes light? I always like to do this. Again, we could maybe dim the lights just for a minute. And we have here accelerating. This is a very high voltage, and there's a low pressure inside this tube, and so therefore, and there's a high voltage. And it's actually a voltage of about 20 or 30,000 volts, but it's also at a very high frequency of about 40 kilohertz. That's what's happening in here. And the reason it's at a high frequency, we'll also show you in just a minute of why that's important for this actual apparatus. But we see that there's actually some colors going on here. Those colors are because they put some phosphor inside this tube. And just like you were showing earlier with the ultraviolet light exciting up the phosphor and make colors, that's what's causing these colors, is those high charges hitting that. But if I just, if I have that and if I just touch my finger somewhere, you can see the electrical charges just come straight to me. That's because I'm at ground potential. This is at 20,000 volts. That current is actually going through me. It's a very small current, though. But how can the current go through glass? Some of you might remember a circuitry and capacitors, and that capacitor is a conductor, two conductors separated by an insulator. And if you have a capacitor, AC currents can go through a capacitor with capacitive reactance. Is that all okay? Or everybody's going like, you're out of your mind. Okay, but anyway. That's why I can conduct electricity through glass, because it's AC. And that's why it's important to have the high frequency. So when somebody touches it, that happens. But another fun thing happens is there's this big electric field here. And if that's at high potential and this is at low potential, you could actually light up a light with it. So these plasma sculptures, if you ever see them, you should pick up one for your classroom because they're just too much fun. And then you can actually teach electrical circuits because you've got a high potential here and a low potential here. And if you take the high to low, you actually got to you have a current, okay? But if I put my other hand at the same high potential, it won't light up now because both my hands are at the same potential. My feet are at ground potential, but my hands are at the high potential, okay? And then if I let go of this, then there's a difference between this hand's potential and the ground, so it lights up again. So anyway, it's a bit of a rock and roll concert and lights again. It's the human circuit, I like to call it. Anyway, okay. But what's important about MaxLab and about light again is it's these accelerated charges. It's a high voltage which makes electrons move. And it's those moving electrons that is giving off the light. And that's what's always important to understand of how light is manufactured at a place like MaxLab is you accelerate electrons and then you make them, you have them traveling along and then you accelerate them. And as long as those electrons get accelerated, that's what causes the light. So we wiggle them and we turn them and we do all these various things to get the light to come out of Max. So that sort of shows what that is about. All right. Let me look over here and see if I wanted to do anything else that I've sort of forgotten. No, I think I'm right on cue here. So the other thing I want to talk about, let's see, turn on the lights a minute, and I want to show a couple of things. We also have something called the photovoltaic cell, okay? And the photovoltaic cell takes light and turns it back into electricity. That's what and this is all due to photoelectric effect, and you guys, from what I've been talking to, understand about the higher energy was related to the frequency, and that was all part of that stuff. But anyway, but a photovoltaic cell was actually able to make visible light and turn it back into electricity. And if you just take a photovoltaic cell and you put an electrical connector on it, you can actually have some fun as long as you have some type of higher gain amplifier. These amplifiers will work a little bit. You'll hear sound come out, but it's not very loud because the voltage coming out of this is rather low. It's not very high. And these things just want a little bit of a higher voltage. So if you ever if you go to Technique or various places, they have these little battery-operated guitar amplifiers. These things are really cool. They usually cost about, I don't know, 70 kroner? I don't know, maybe more than that, something like that. No, they're a little more than that. Maybe 170 kroner or something, 120 kroner. Anyway, so I just put the photovoltaic cell on a guitar plug. I plug it in here, and I turn this on, okay? And I can pick up lights like that bright light there, and if I cover my hand, you can't hear it, but that light's doing some stuff. I could actually play with a laser here and actually, anytime the laser hits it, okay? So you can do that with visible light. You can actually have the laser hit it and do some other silly things like put a comb in front of it. Okay, yeah, that's fun. Okay, and then, so now if I've got that and I've got some way of maybe controlling some intensity of light, we can actually start showing something about communications, okay? And in a little bit, before you leave here, in the last 10 minutes, we're going to try to have you build a circuit to take with you, okay? And that circuit is going to be consisted of a battery, a resistor, a capacitor, and the ability to hook up to like an iPod and an LED. There you go. So we're going to light up the LED, but we're going to have a little resistor here in series. And what we're going to try and do is get the voltage from the iPod to go across this resistor here. And if you remember your simple circuits, if you change the voltage here, you're going to change the current flowing through here, and therefore that's going to change the brightness of this LED. You can't see the light coming out of this, but this thing can hear it just fine. That's the infrared remote controls that control your TV sets. And also there's even black plastic that you can't see through, but the infrared goes through just fine. Because this is an infrared passing filter, so it'll pass light you can't see, but black you can see. Crazy, but it exists. Okay, and then, no, I don't want to even get there yet, because even though my one light, the one light I was going to do, but well, let's just make sure everybody has got one of these before you go home. So make sure that you may have already picked these up because I was giving some of these out at this station here, but just go ahead and grab one of these Does everybody not have one of those? They're just a diffraction grating. And you can see spectrum through it. Okay? And you should just have one of those, because I was going to do a thing with these lights to show you the spectrum, but they don't light up, so I still can't believe they're not lighting up. Silly things. Light up now. Okay. Anyway, all right, so we've got this light. Oh, yes, I wanted to show you. I can actually show you the light you cannot see again if I just go back to this. Oh, this thing is actually picking up the light from the... Isn't that amazing? You can actually have these things talk to all kinds of light. Anyway. Here is me. Hi. And here's the remote control. And if I push the button, you can see the light coming out of the end. That's the infrared coming out. So any of your CCD cameras, the cameras in your cell phones and your students' cell phones, most of them. Some of them are actually blocking the infrared now. They've actually put better filters in. But most of those, some of the iPhones are actually blocking pretty good. But if you just have your students take an infrared remote control and have it pointed at their cell phone, do it tonight with your children or your friends, you know. The next party you're at, you know, just tell people, oh, look, you have a remote control. Pull out your cell phone. I want to show you something. Look, you can see the infrared if you just shoot it to your phone or your digital camera. Digital cameras work even better than cell phones sometimes.
So try to the camera, please.
Pardon?
Try it to the camera, please.
Try it again.
I can pick it up.
Let's see if I can. There we go.
To this camera, sorry.
Oh, that camera.
Yeah,
Let's see if it'll, I don't know. Will it pick it up? Does it pick up infrared? No, it doesn't. No. No, they've got a good infrared filter, because if you could pick up infrared, it would actually kill some of your other abilities. Okay. A lot of cameras, there's a Sony video cameras at home won't do it, but then they have a thing called night shot. And if you turn the night shot on, then you can see it, because it'll let all the IR in. All right. Okay, so now what? I was over here, and I was going to send some music. Let me think if there was anything else I wanted to show you before that, because I want you to be able to build that. So I think I've shown you enough, given you some ideas, and now we'll just play music. Okay, here we go. So, oh, and now, but yet again, well, here, we'll just do it here for a second. So let's see, play. Let's see if it's working. There we go. So, but again, you guys are just sitting a little bit too much, so let's make it just a little more exciting, because, you know. So we'll just take this thing here, and then if you want to make it just so everybody understands and dances a little bit more, we can take this output here, because now it's a very good output, and I can take this and, oh yeah, okay. There we go. There. So now you're supposed to clap, but I'm not blocking it. The music stopped, but so if I just block it, it just stops. It's laser communications and light communications. You can play with your students. Okay, anyway, you get the idea. So, okay. So now what we're going to do is we're going to have you make one of these per following instructions, okay? So the circuit, maybe we could turn on all lights now, I think, so everybody could see really well. So the circuit is nothing more than the battery. So see how well you guys remember your circuits. A resistor. This is the LED. And goes back like this. Actually, yeah. Actually, I do it the other way, I think. Let's do it this way. There we go. And then we come over to here. This is the input from the iPod input. Okay, and then it's going to come to a capacitor. And just to let you know, I will explain it in English very quickly here. The whole idea is, so this thing goes around and lights the light bulb. This causes a voltage to light up. This coupling capacitor, that capacitor is just going to make it so no current will flow through whatever apparatus you're connecting to it. So you wouldn't want to hook up somebody's iPod and burn it up. So that's just a protection device. And for the most part, it'll work. So now, let's everybody try and follow instruction. Now wait, how many people, who has worked with wires and putting things together before? You? Anybody else? Why don't you join a table that doesn't? Is there a table that's never wired up in their entire life? Okay? Just try and split up in ways that maybe somebody will understand a little bit of components. All right, so the first thing I want you to do...
Sen.
Yeah.
Sen. Just one second. Just
Yeah.
one second for the camera. Det vi har delat ut nu, det är lite leksaker här inne i muggen som ni ska använda för att bygga er egen. Och så en sån, va. Så tanken är att ni ska bygga er egen och ta med hem.
So the first...
Vad sa du? Du fick inget sånt.
So the first thing I want to do, Lasana, let's try to, you can translate just to make sure everybody gets it. So take their LED and find the longer, there's two leads. There's a long one and a short one. Find the longer one. The longer one.
De här diodlamporna, de har två ben. Ett som är lite längre än den andra. Det är en som är plus och en som är minus. Om man pluggar in det åt fel håll så lyser de inte. Och då märker ni vilket som är fel och vilket som är rätt.
Okay, and then you take the red wire from the battery, okay, and you just put them both, just line them up so they're very, very close together. Yes, like this. And then take the gray nut, the wire nut, and push them both in at the same time, push them in, and then just turn clockwise, yeah? So have fun explaining that.
Det finns såna här sladdkopplingsaggregat. Igår tittade jag på Klaus Olsson. De var lite stora, lite för stora och lite dyra. Det är bara för att sätta ihop kablar liksom och så, va. Antingen ska man ta en sån, eller så finns det såna här vita, ja precis, med skruvmessor liksom. De funkar lika bra, de är mycket billigare. Men såna här är lite snyggare. Yes.
Loose would be counterclockwise. Tighten.
Can you take it off?
Yeah, you could take it off.
Det går upp.
Yep.
And which one is the
now
longer one here?
Now the other one is minus is going. Oh, now they need to grab the resistor, which is this nice thing with little colors on it. The resistor, okay, and the capacitor. This is the capacitor, and that's the resistor. Okay, and then we take one lead of the capacitor, one lead of the resistor. This is so much fun. And then, where did I just put it? The battery, here it is. Okay, and, whoa, come back, don't drop it. No, just teasing. And then you hook those two to this, so there's 3 wires now. The other wire of lampa to one side of the resistor and one side of the capacitor, so 3 wires.
Alla med. Vi har kondensatorn och resistorn och från batteriet, alla 3 tillsammans.
This one and this one.
En i samma ingång.
All 3, yes? Anybody? He's getting his all starting up there. So then you do all 3, and you twist those together, and hopefully they stay together. Ta-da! You want to go around and make sure they're...
Yeah.
I'll just take it around to them.
Så här ser det ut, va? Från... Ni är klara? Okej. Här har vi de 3, va? Från röd, så plus från batteriet in till lampans plus. Och sen lampans minus tillsammans med kondensatorn och resistorn.
Det spelar ingen roll vilket ben på kondensatorn.
Nej, det spelar inte så stor roll.
So now you take...
Kolla lite.
Are we all set yet? Pretty much. There's this wire here. There's this black wire. And there's a center, the center conductor, not this blech, but this nice pointy thing. And you put it to the other side of the capacitor, and you screw that one together, like so.
Så ni sätter ihop kondensatorns andra ben tillsammans med högtalarsladden, va? Hörlurssladden. Den centrala delen av hörlurssladden till kondensatorn.
Back to the condenser, yeah? What do you say, capacitor or condenser?
Man kan sen rita en karta av det här själv, hur man kopplar. Vad sa du? Ja, kopplingsschema, va?
Okay. Aha! Yeah, they got it. Okay. The last one, there's the last 3 wires. So you got 3 wires, should have 3 wires left. The black negative from the battery, the other side of the resistor, and then that shield. And then you try to take those and twist those 3 together. And it's probably the hardest connection to make. We need to...
Du ska...
Yeah,
ni behöver
so
en
you have the
sån.
resistor to plus. So you put it...
Spelas får vi se.
It was a good experience. Science rocks. Science rocks? Science rocks.
Yeah.